All right, guys, let's talk about parallel lines and proportional parts. In this lesson, we're going to use what we've been learning about similar triangles, and we're going to extend those to working with parallel lines because we're going to see that there's really similar triangles often hidden in parallel lines. And when we do that, we can use proportional parts to solve triangles and lots of other problems. We got some new vocabulary here. Mid-segment of a triangle. This is going to come up. And a mid-segment of a triangle is a segment drawn within a triangle that has its endpoints on the midpoints of two sides of the triangle. So if I took this side of this triangle and I divided it in half, I dropped a point there at the midpoint, and I dropped another point here at the midpoint of this side, making these two segments congruent. If I connected them, I would have what's called a mid-segment. Looks kind of like our mid-segment from the last chapter on quadrilaterals, mid-segment in a trapezoid, right? It's the same idea. We're going to learn more about it, but when you have this condition, turns out mid-segment will be parallel to the base that it's drawn to, and it'll always be exactly half the length of the base. If this base was 2x units long, your mid-segment's going to be x units long. Okay? All right, we also got to talk about triangle proportionality theorem. If we have a condition like this, and if a line is parallel to one side of a triangle, notice BE is parallel to CD, and it intersects the two other sides of the triangle, then it divides these sides into proportional parts. It's going to divide this side into segments with proportional lengths. So, in other words, if BE is parallel to CD, then AB over BC, this segment over that segment, will be the same ratio as this segment over this segment. AB over BC equals AE over ED. How do we know this is true? Well, if these lines are parallel, take a look. Those angles are congruent, are they not? We could think of AD as a transversal with these parallel lines. What's the relationship between those angles? Those are corresponding angles. Likewise, I got corresponding angles hanging out over here. And now I can see I have angle-angle similarity, and triangle ABE must be similar to triangle ACD. And now it makes sense that there would be proportional parts hiding out inside a figure like this. Okay, could we try a problem like this? In triangle RST, they're telling us that RT is parallel to VU. They've marked that. These two segments are parallel. They're saying that SV is 3 units long, VR is 8, UT is 12. Could we find SU? Okay, well, if these segments are parallel, well, if you want, you can prove it to yourself. I got corresponding angles there. I've got corresponding angles there. We know corresponding angles are congruent when the lines are parallel. And so we've got similar triangles by angle-angle similarity. Okay, so I can go ahead and set up a proportion. I like 3 over 8. 3 to 8 should equal x to 12. Okay, but perhaps you came up with a different proportion. Did anybody look at it and say, hold on, could I say 3 over x equals 8 over 12? Are those equivalent proportions? Let's take a look at the cross products and see. 8 times x is my cross product up here, and my other cross product is 3 times 12. Equals 3 times 12. Notice down here I get the same cross products. 8x equals 3 times 12. So those, in fact, are equivalent proportions. The one thing you want to be careful of is don't get them crisscrossed. Don't say 3 over 12 equals x over 8. That's going to mess everything up. That's not a valid proportion. That's not comparing corresponding parts in these similar triangles. So let's go ahead and solve this one. 8x equals 3 times 12 is 36. I'll divide both sides by 8. And I'll get x equals 4.5. Okay. Does that look right? That looks about right. Let's try another one of these. And by the way, if you guys aren't in the habit of just pausing the video, if you want to try a problem like this on your own before you hear me explain it, that's a good habit to get into. You can go ahead and pause the video. Here, triangle ABC, we have AC parallel to XY. And AX is 4 units long, XB is 10.5, CY is 6 units long, and they want us to find BY. Okay, well, with those parallel lines, I recognize that we've got those similar triangles hiding out in there. I know that theorem that we just learned tells us that 4 over 10.5 should equal that over that, should equal that over that, should equal 6 over x. Good. My cross products are going to be 4 times x equals 6 times 10.5. Okay, so I get 4x equals 63. And I can divide both sides by 4. And I get x equals, what, 15 3/4? Is that right? 15.75, if you like. All right. As you probably know, some of our best theorems in geometry have converses. And this is our converse of triangle proportionality theorem. It tells us that if we've got some line that intersects two sides of a triangle such that if I check the proportions, let's say they gave me all these values. If AB over BC equals AE over ED, guess what I conclude about these two lines? I can conclude they must be parallel. They must be parallel because if these parts are proportional, then these triangles must be similar. And if these triangles are similar, then all of their angles must be congruent to one another. And if these angles, this angle is congruent to that angle, and this angle is congruent to this angle, guess what? Those lines are parallel. Let's try some examples. Here, in triangle DEF, they're telling me DH is 18, HE is 36, DG is 1/2 of GF. Okay, how could I express that? DG is half of GF. How about I call GF 2x? If DG is half of 2x, what would that be? That'd be x, right? Okay. Could we determine from that information whether GH is parallel to FE? I'm going to go ahead and highlight this so we can keep our eyes on the prize. GH over FE. Are those parallel? Well, these segments would have to be proportional if those lines were going to be parallel, right? So could I set up a proportion? 18 over 36 should equal x over 2x. Okay, and maybe you already see that these fractions can be simplified, right? 18 over 36 is 1/2, isn't it? And x over 2x, don't the x's cancel and I'm left with 1/2? Okay, that looks like a valid proportion to me. Can I conclude that these lines must be parallel? Absolutely. Let's try another one like that. Here in triangle WXZ, they're telling me that XY is 15. I'll go ahead and mark that. YZ is 25. WA is 18. And AZ is 32. Okay, could we determine whether or not AY and WX are parallel? Okay, could we set up a proportion and see if these segments are actually proportional to one another? What would that proportion look like? 18 over 32 should equal 15 over 25. Okay, and if you want, sometimes it's easier just to reduce these fractions to simplest, to lowest terms before you start to cross multiply. You'll be working with easier numbers. 18 and 32, both top and bottom here are divisible by 2, right? I can reduce that to 9/16. And 15 and 25 are both divisible by 5, so I can reduce that to 3/5. Okay, if these two fractions are in lowest terms, and they're not the same, then they're not the same fraction. And so this is not a valid proportion. If you wanted, you could go ahead and cross multiply. You'd find your cross products are not equal here. 9 times 5 is 45. 16 times 3 is 48. So if this is not a valid proportion, then these segments aren't proportional. And if these segments aren't proportional, well, these lines aren't parallel, right? All right, let's tackle triangle midsegment theorem, okay? As I described earlier in our new vocabulary, a midsegment of a triangle is it's parallel to one side of the triangle, and its length is exactly 1/2 the length of that side. And you construct it by drawing it from what midpoint of one side to the midpoint of the next side, okay? So if we have a midsegment, if I know that these segments are congruent and those segments are congruent, I know DE is not just any old segment, it's a midsegment. I know it's going to be half the length of BC, and I know it'll be parallel to BC. Let's try a couple of examples. Here in this figure, DE and EF are midsegments. Okay, I'm going to highlight these. I'm going to highlight DE. That's a midsegment. I'm going to highlight the side that it's parallel to, because that's significant. And EF is also a midsegment, so I'm going to highlight that in orange. I'm going to highlight the side that it's parallel to in orange. Hopefully this will be a little easier to picture that way. They want us to find a couple of things here. A, B. Okay. Well, if ED is a midsegment, don't forget it's exactly halfway between the base and this opposite vertex. And as you might suspect, that makes it exactly half the length of that base, AB. So if ED is 5, AB must be 10, right? It must be twice that length. Good. Could we find FE? Okay, FE is a midsegment here, parallel to this side BC. This is its base. And if it's going to be half the length of that base is 18, FE must be 9. Good. Okay. Could we find the measure of angle EDC? This angle right in here. Okay. How would I find that angle? Well, don't forget, there's something else we know about midsegments. We know that these guys are parallel. Midsegment is parallel to its base. In this midsegment, FE is also parallel to its base. Okay. So, if these segments are parallel, how am I going to find this angle over here? Do I have some corresponding angles, perhaps, that I could work with? Do I have some alternate interior angles? If these two lines are parallel, isn't ED a transversal? And wouldn't that make this angle and this angle alternate interior angles? And when the lines that form them are parallel, the alternate interior angles are congruent. So that's going to be 87 degrees. Okay? Let's try one more example like that, and then I'm going to break this lesson into 2 parts. And the second part we'll pick up on, we're going to talk about proportional parts and parallel lines. Let's do one more of these midsegment problems. In this figure, DE and DF are midsegments. I'm going to go ahead and mark everything I know about that. DE and AC must be parallel, and then DF and BC must be parallel. Okay. Could we find BC? Okay. Well, if DF is a midsegment and it's parallel to BC, then BC must be twice as long as DF. So this must be 16. Okay. Could we find DE? Well, if it's a midsegment, it's going to be half as long as that base that it's parallel to. Be half of 15.5. It'll be 7.5. Good. And could we find the measure of angle AFD? Let's see, what do we got here? AFD, that angle right there. Okay, well, take a look. This line is parallel to that line. This line segment, excuse me, is parallel to that line segment. And if this angle is 122 degrees, these guys are alternate interior angles. They're on alternate sides of the transversal. They're on the interior of these parallel lines. So this guy must also be 122 degrees. Okay, all right, don't forget to watch the second half of this lesson. We're going to talk about proportional parts, parallel lines.